Okay, Bismillahirrahmanirrahim. And the Gauss law, and today we have to done some numerical example for the Gauss law. Okay, so the first example is a very simple example. A line charge is extended along the z-axis. Okay, find the total flux leaving a 5-meter length of the line charges. The line charge density is 8 nanocoulomb per meter. Okay, so the line charge density is given, the length is given. Okay, and we have the cylindrical shape, so we have to find the total flux, means the psi. Okay, so applying the Gauss's law, psi is equal to d dot ds is equal to q enclosed, as line charge density is equal to q by l. So replacing uh, q by rho l into l. Okay, rho l into l, cross multiplication. So q is equal to the rho l is given 49 8 nanocoulomb and l is 5, so we will get 40 nanocoulomb. This is the q. So according to the Gauss's law, psi is equal to q enclosed, as these charges are enclosed in that cylinder. So uh, the tr- the q is equal to the total flux, means 40 nanocoulomb. We have the flux line equal to 40 nanocoulomb. Okay, so the next example is, we have the q 25 microcoulomb, and we have to find the flux. Okay, so q will be equal to flux only if and only we have the closed surface. Okay, so now we have in a part we have the portion of sphere, not the complete sphere. So we cannot say that q is equal to psi. Okay, this is only applicable if we have psi is equal to q enclosed in a closed surface. Okay, so this is not applicable in a portion of sphere. Q is equal to psi is not equal in portion of sphere. Okay, so uh, r is equal to 20 centimeter, theta is ranging from 0 to pi, and phi is ranging from 0 to pi by 2. Now we have the second part is the closed surface. Now we can say in advance that as we have the closed surface, so the psi will be equal to q, because we have the closed surface. The C is the plane sheet. Okay, so let's have a start from the part A. Okay, we have a portion of sphere, and psi is equal to d dot ds. D is equal to q dot by 4 pi r square, and that is understood in the direction of AR in the spherical coordinate system, and in the direction and it will be directed in the along a rho in cylindrical coordinate system. So and this is the ds in the direction of AR in spherical coordinate system. So this is d, this is ds. Taking the dot product of these two, we will get q sine theta d theta, and this 1 over 4 pi will be taking out of this integration, applying the limits on respective variables. For phi we have 0 to pi, and for theta we have 0 to pi by 2, that is given. So we will get q is equal to q by r, psi is equal to q by r, as q is equal to 25, so 25 over 4 will be equal to 6.25 microcoulomb. Okay, here we have a closed surface in the form of a cylinder. While the charge is located at cylinder, the cylinder is extended from 0.5 meter to 0 0.5 minus 0.52 plus 0.5 meter along a z-axis, that is given. So we have psi is equal to q. Okay, psi will be equal to q, which is equal to 25 microcoulomb. Okay, because of charge enclosed, we have the closed surface. Okay, now part C. we have a sheet. So okay, so we have to consider that uh, we have two parallel sheets. The one is along this, okay, and the other is like this. These two are parallel sheets, okay, and the charge is enclosed in that sheet, and some of the flux lines are passing on the upper sheet, and some of the flux lines are passing uh, to the downward sheet. So as we have given that we have one plane only, so we will consider either of top or the bottom plane, okay. So as I have told you that half of the flux lines are passing through the upper side of the plane, and the half are passing through the lower side. So we have psi is equal to q by 2, because from one sheet we will get half of the flux lines. So the answer will be equal to um, 25 divided by 2. Okay, that's it. 12.5. 12.5 for one plane sheet. Okay, 12.5. The next example is we have to find D. Okay, at this point 6 8 minus 10 in rectangular coordinate system. So this is actually the x, this is y, and this is the z. Okay, and we have a point charge, the line charges, and the surface charges. In A part we have the point charge that is equal to 30 nanocoulomb. In B we have the line charges in that is equal to 40 microcoulomb per meter, and we have the surface charges that is equal to 57.2 microcoulomb per meter square. Okay, so as in rectangular coordinate system, d is equal to q into by 4 pi r square, and in the direction of ar unit vector. Okay, so unit vector, as we know that unit vector ar is equal to vector, position vector r, okay, divided by the magnitude of that position vector. That will be a unit vector. Okay, so d is in the direction of ar. So first we have to find ar. Okay, so this is actually the d. Now what is the unit vector ar? This is r, uh, 6 minus 0. It means the q is located at the origin, and we have the point of observation at 6 8 and minus 10. So 6 minus 0, 8 minus 0, and minus 10 minus 0. Okay, so we will get this is r, and now uh, we have to find the r magnitude, means 6 square plus 8 square plus 10 square whole square root. Okay, so we will get 14.14. So now the position vector will be this. Okay, and this is actually the d. Now in b part we have the we have to find the d, and we are given the row l. Okay, so the points are in rcs. So let we have consider the d in ccs. Okay, so rho l over 2 pi rho. Okay, so now the given point is 6 8 minus 10. This is in rcs, so we have to convert this rcs in ccs. So rho will be equal to r square plus y square whole square root. We will get 10 for the row, and for the phi, tangent inverse y by x, y is 8, x is 6, so we'll get 53.13. And z of rcs is equal to z of ccs, so no need to convert this z. So d will be equal to this. Okay, 2 pi, this is a row. Okay, so we will get 63.66 into 10 to the power minus 9 in the direction of arrow. Okay, so dx, dy, dz, transforming into RCS. Now again transforming this into RCS. So cos phi minus 1. This is the procedure of transforming from CCS to RCS. So we will get this in the direction in this is the dx value and this is the dy value. Okay, and dz is 0. Now the third part, as you know that rho s okay, this is the similar example as we have done in the previous one. Okay, we have a sheet, so we will get the half of the charges from that surface. Okay, so we will get d is equal to rho s divided by 2. Rho s is this 57.2. Okay, uh, and divided by the 2, this is given. Okay, 57.2. See this is 57.2. Okay, and this lies on a plane, so as I have already told you that we will get half of the flux lines from that plane. So we will get 57.2 divided by 2. Okay, and this is in the direction of minus ax, so that is why we have the minus sign with this answer. Okay, so this numerical has been over. Now we have this example. Okay, this is not the part of the previous example. Okay, ignore this one. This is the new example. This example of coaxial cable. Okay, a 50 centimeter coaxial cable, and the inner diameter is 1 mm and the outer diameter is 4 mm. We have to calculate the internal feed when the free space between the conductor is assumed to be filled with air, and the total charge on the inner conductor is 30 nanometer. Okay, so now the data is L is 50. Okay, inner conductor is 10 raised power minus 3. B is outer conductor radius is 4 into 10 raised power minus 3, and the Qn charges on the outer surface of the inner conductor is 30 nano coulomb. Okay, so as we know that Qn is equal to, we have already proved this Qn previously, so directly use that relation. Qn is equal to rho s n 2 pi al. A is the radius of the inner conductor, so rho sn will be equal to q sn divided by 2 pi al. Q is given, that is 30. 2 pi a is given 1 milli, and l is given 50 centimeter. So this, okay, rho sn is like that. Now for we have to consider the point of observation in between a and b, as d is equal to a. This relation has already been mm, already been proved previously, so directly a rho s over rho. Okay, so a is 1 milli, rho s from here 5.99, and rho is not given, so rho is actually the radius of the point of observation of the we can say that the radius of the Gaussian surface. Okay, so d is equal to, in term of rho, will be equal to 9.99 into 10 to the power minus 9. Okay, now d is equal to epsilon naught e. E is d by epsilon naught, so dividing this whole equation by epsilon naught, we will get 1079 by rho. Now this is the condition if the point of observation is in between A and B. And what will be the situation if we have the point of observation out of the outer conductor and inside the inner conductor? So we have discussed this already in the previous video. Okay, okay, now we have a next example, and that is the homework for you people. Now this is simple. Actually we have uh, row s1, row s2, and row sx. Okay, three surface charge densities. The rho s1 is having a radius of 3 centimeter, rho s2 has having a radius of 5 centimeter, rho sx has a radius of 7 centimeter, and we have to find the d at different points. Okay, so if we have one surface, two and three surface, and the point of observation is at 2 centimeter. Now the point of observation is at 4 centimeter, the point of observation is at 6 centimeter, and point of observation is at 7.3. So this is very simple. If we have the point of observation inside the inner conductor, so the q will be equal to 0, because the according to Gauss's law, the the psi will be equal to the charges enclosed. So if we have the point of observation inside the inner conductor, so there will be no charge enclosed in that Gaussian surface, so this will be equal to 0. And similarly, if we have the point of observation outside greater than the outer conductor, so the same case we will have psi will be equal to 0, because in the Gaussian surface the plus q will be equal to the minus q. The magnitudes are same, so we will get 0 answer after the summation of these two. Okay, and if we have the row somewhere in between a and b, then we have to find the d according to this procedure, the previous example. Okay, so now this is the homework for new people. If you have any difficulty, you can ask in the group. Thank you.